It actually does. Oh, very good.
Okay. So we are very glad for Finn Larsen from the University of Michigan to start this program by telling us about the instability of extremal black holes in AdS supergravity. Over to you, Finn.
Thank you, Suvrat, and thank you, well, for all the people here. And it's wonderful to see Spentas Institute in actual reality. I saw it in 2016 in String 16, where it was, well, a vision, beautiful vision, but to see it in reality it's wonderful, and it's a beautiful place, and I hope to come back again. So I was asked to do a discussion, but in case there are any members of the consular services around, I can't take that risk. I've been strictly asked to do a pedagogical lecture, and my passport says I cannot depart from my original plan. So, so I will give a lecture and not a discussion. At any rate, so it will not be quantum at all, actually. I will talk about classical stuff, but it is black holes, which was one part of the topics of this meeting. So here we go. I'll first do a bit of very top-level introduction, pedagogical it will be. So black holes, they are parameterized by conserved charges. This is kind of how we distinguish between different types of black holes. What charges do they have? For example, what angular momentum do they have? What charge do they have? Electric charge, Q. Well, the extremal limit of a black hole, corresponding to imagining a family of black holes in your favorite theory, that family will depend on these charges, but they also depend on the energy. And the energy, if you take that to be the lowest possible within your family, that's called the extremal limit. So that would be an extremal black hole. It's the lowest energy black hole in the sector with those given conserved charges. So the extremal black holes are very important, but there are two intuitions that, at least in my mind, are a little bit contradictory and that I think is sometimes being used in various contexts. And they're conflicting. One is that, well, didn't I just tell you that you kind of take the lowest possible energy? So it's some kind of ground state of the theory. That's what an extremal black hole is. It's a ground state. And you might think that because it's a ground state, it should be particularly stable because, you know, it's the ground state. On the other hand, a way to think about the extremal black holes is that the black holes are kind of made out of stuff. It's made out of the stuff that these charges are, like maybe they're made out of things with electric charge. And in fact, the extremal black hole is such that it's exactly on the boundary where these electric charges are about to repel, so that they're about to fall apart. From that point of view, you might say that a black hole is simply the boundary to an unstable phase, that's what an extremal black hole is. So, which is it? Are black holes that are extremal ground states? Or are they things that nearly fall apart? Well, we get some guidance if we're in a theory that has supersymmetry. Then the charges, they form an algebra of some kind, and quantum states, they form representations of that algebra. And that gives you a notion of what energies are allowed. There's a unitarity bound in your quantum theory that says that the charges, whatever they are, in the sector of given charges, there's a set of energies allowed, and there's a lower bound of the possible allowed energies that are allowed by quantum theory by itself. It doesn't necessarily have anything to do with a black hole, but that is some kind of bound that you can go and compare with what about the black hole bound? There's a lower bound given these charges based on basic quantum principles, and there's a lower bound among the family of black holes we have been able to find. Well, saturation of this unitarity bound corresponds to imposing additional conditions on charges. The unitarity bound is stronger than just being the lowest possible energy in the given sector. The energy has to go down and be particularly low. Supersymmetric black holes are a special type of black holes, and they're the black holes that saturate the unitarity bound. So there are large classes of black holes that are extremal, as in they're these kind of ground state-like things, but that are not supersymmetric. And those are the ones that I'm interested in. So the paradigm that I'm interested and going to advocate for and develop a bit is that actually instability wins. Instability is generic. Supersymmetric black holes, they're stable, but they're rare. They correspond to putting on additional conditions. So you must put extra conditions on your continuous parameters in order to get supersymmetry. If you do not put these things on, you have extremal black holes, but they're not supersymmetric, and they will be unstable. There's been a lot of discussion, especially in connection with JT gravity and other more, specialized studies along those lines, that there are quantum instabilities that are important for this problem. And that's true, but the instabilities I'll talk about are actually much worse. They're completely classical. And there's no barrier. So they're fast. The decay products and the decay mechanism and the end products, it will depend on the details as to what theory we're in. So there's a lot you can consider. But the general argument is this one. Non-supersymmetric extremal black holes are classically unstable. There is the story for the near-extremal black holes that's interesting. There are interesting stories with the quantum effects. I just won't go there in this talk. Classical instability. Let me give you an example so we know what we're looking at. 40 black holes in flat space. Textbook. Reisner, a Kerr-Newman black hole has mass, but it has a charge, electric charge Q, it has an angular momentum J, and a mass M. To give you something, this is the entropy, so it's the area of the black holes. I'm not giving you the geometry, which is a bit ugly to look at, but basically the area of the horizon. Now you can go and check that this is a continuous family, of course, of masses, but when the mass gets small enough, the square root here goes negative. So therefore, there's a lower bound on the mass in order for that square root here to go down to 0. When the mass is lower than that, the area would somehow become imaginary, you'd suspect that the solution don't exist, and you'd be correct. So the lowest possible mass is where that square root goes to 0, and that gives me this bound on the allowed masses. Black hole solutions simply only exist for continuous masses, a continuous range, but lower bound here. So the lower bound equal to is the extremality, the extremal black hole. What about supersymmetry? Oh, supersymmetry is much stronger. It's not enough that you have the mass equal to this. Oh no, you must also have J equal to 0. Rotating black holes in flat space are not supersymmetric. They can't be. So it's an extra condition, it's much stronger. In flat space, it may seem like, yeah, but I didn't look at rotating black holes anyway because it's complicated. Yeah, okay, but it was something that was also a thing that was actually forced upon you by supersymmetry, not just by taking the path of least resistance. So if you look at this example here, because this is my intro, looking at, well, so what happens if these standard black holes here that are asymptotically flat black holes in my textbook, are they unstable if they're extremal? Will they in fact fall apart? If so, to what? Well, that's the hypothesis. Extremal black holes without angular momentum, or with angular momentum being non-zero, sorry, so with angular momentum, they're unstable. Well, one thing that can give you an idea about why that would be is to look at the Hawking radiation. Now, Hawking radiation, I promise you to say no quantum here. It's quantum, Hawking radiation. But actually, it has a part of it that's classical. And you see it very easily from the Hawking spectrum. This is the Bose-Einstein distribution. There's some gray body factor here that says it's not actually precisely the standard Bose-Einstein. Depending on energy, the radiation comes out. But the important part of this formula for these purposes is just the Bose-Einstein factor down here. There's a rotational velocity of the black hole sitting here. Now it is clear that if the energy of the quantum that is being sent out goes so low that this thing is below 0 or below, then this diverges. So the rate of emission, as it stands, diverges at very low energy. So clearly, this formula must somehow be wrong. The interpretation of this phenomenon is what is called superradiance. It predates Hawking radiation, and that was actually in part what led Hawking to find Hawking radiation, the quantum version of this. But the classical part of this, the one that says this one just blows up, is the instability that we're talking about. It's not the only instability we're talking about, but it's one of the instabilities we'll talk about, is that this thing here will blow up, even if the temperature here is very, very low. Once this thing here has become infinite, this one here will kill you. This is a thing. It's been understood for or at least discussed in the literature for decades. Oh, yeah.
So just to say what you said in different words, are you saying that the supersymmetric black holes, if they have J positive, they're non-extremal and they're unstable?
I don't think I said such a thing. Supersymmetry is simply only possible when J is 0.
Okay.
Therefore, if I'm discussing J not 0, I'm not discussing supersymmetry.
All right.
Period.
Okay.
I could try to cut my cake in a different way, which would have to do with, focusing more on the supersymmetry. But in a way, I'm taking the view, which is what I started with, I'm interested in extremal black holes.
Okay.
And nearly all extremal black holes I'm interested in, I'm just not interested in the supersymmetric ones.
Okay.
They will be a special case, but they require extra fine-tuning. Kind of like rotating black holes. Well, a special case of rotating black holes is when the rotation happens to be 0.
Okay.
So generally, no supersymmetry. But there's a notion of ground state, because it's the lowest energy.
And in this case, for extremal black holes, beta is what?
So this slide here actually indeed is not really good for extremal black holes. This is better understood as an instability that actually is true even near extremality. It does have an interesting limit, but you're correct that the way I present it, that doesn't really fit. You're correct. Yes. Exactly, and I will be very explicit about this, or I will, somewhat explicit, that yes, they will be super radiant. Extremal ones will be. So even though they're sort of not supposed to radiate anything, they radiate a lot. There is a notion that's called black hole bomb. Basically, that if you send in particles towards your black hole, then they mostly get absorbed. Black holes are pretty famous for absorbing the stuff that comes in, but some of it might reflect back. The process we're talking about here is the special case where the amplitude of what comes back exceeds what you're sending in. So it's actually an amplification process. Energy is extracted from the black hole. I say this as if it was a scattering process, but the Penrose process is another one that's being sort of in the textbooks for how to do this, and that is pretty much what I'm talking about. You can extract energy from the black hole if you lower the rotation, as in bringing it closer to supersymmetry. It's getting more stable as you go closer to the supersymmetry. So if you think about a rotating black hole that, well, I'm saying that you're in a asymptotically flat space, but if you imagine that your asymptotically flat space is in a finite box, it's big, but it does end somewhere just to make the entire radiation bath having finite energy, then whatever is being emitted will get reflected back in the black hole and then amplified and go back out again and amplified and so on. So in other words, the entire black hole will end up emitting more and more of its energy. This is the black hole bomb. Works great for funding agencies.
I have a question.
Yeah, I mean, you're experts at it. You guys are, part of the, nuclear or whatever, something.
I have a question, actually. Wouldn't you just take this black hole solution and make a small perturbation and find that there are negative eigenvalues?
No.
It won't.
No.
That's an instability also.
The quasi-normal modes here they're not showing it. The quasi-normal modes have only negative imaginary parts. Yeah.
I see.
It's not an instability in that sense, but as Finn was saying, if you throw in a wave, it'll come back with a bigger amplitude. Yeah, it'll extract the energy from it. So
It's
that's
like, it's a laser. You need to get it started, but we will do this in
Quasi-normal
AdS.
modes will have the wrong, but then some of them do have positive, do have the wrong side.
We're on the way to AdS. We will go to AdS. Indeed. Right. Yeah. So at any rate, this is a thing for some astrophysicists. They're hypothesizing and wondering if there are really light scalars such as axions that might in fact do this and have really, really large astrophysically significant signals, and there's some parameter ranges where this would be true. Not at all what I'm trying to do. I will look at examples in AdS3 and AdS5. Somebody said there, yeah, Shiraz has been looking at that too, but still haven't seen his paper, so I may overlap with his paper because I don't know his paper. So, what? Oh yeah, that paper, yes, yes, oh yes, that paper I'm aware of course, yes. But you'll see, that's not supersymmetric, and very far from supersymmetric. So, these are my perspectives. Some perspectives, extremal, not supersymmetric black holes, they're unstable. What do they decay to? Given supersymmetric charges, conserved charges, if there is no black hole that is down there at the lowest possible energy for those conserved charges, well, that means the ground state is not a black hole. Yeah, then what is the ground state? Good question. And what is the CFT mechanism for the instability and for what's going on here if you're in AdS? So those are some of the questions that I will at least in part will answer. Yeah.
about the fact that extremal non-SUSY are unstable, at least as of a few years ago when we tried to look at it in explicit string compactifications and so on, there were cases which were on the edge where you couldn't quite rule it out, you know. And so it wasn't a case that one could prove a theorem every time you get a non-SUSY extremal black hole.
And I'm still not in a position to prove it. Okay. This is the overview, the perspective, but you'll see though that I have some mechanisms that are very clear, that are not on the boundary, that are clearly on the unstable side, including some that were not known previously. And some mechanisms that were claimed to be unstable and that I will actually say, But, well, so that's the outline. I'll talk about thermodynamics for extremal black holes. Then I'll focus on one mechanism, superfluidity. And that requires that I'll look at spectrum of black holes. And then if I get to it, I'll talk a little bit on the CFT side, which is on Bose-Einstein condensation. But that's a CFT mechanism. But I don't have that many slides on that, and they're not that well developed, so we'll see. But first, thermodynamics. Let's just get settled in AdS5, cross S5. I told you just generally that we're interested in what are the charges. Well, in this particular context, our charges is related to the symmetry of the theory. We have an SO2, 4 conformal group. The rank 3 here, so there's an energy, and there are 2 angular momenta within the AdS. SO6 also rank 3, so there are 3 angular momenta kind of within the sphere. So we have a conformal weight energy, we have 2 angular momenta, and then we have these 3 R charges. Almost always, I would take these 3 R charges equal for the purpose of discussion, but in papers, they're not equal. So the asymptotic data of the black holes in AdS5 is the mass, interchangeably energy. There are 2 angular momenta, and there are 3 R charges. It's good to remind oneself that there really are 3 R charges right here, because if you look at the algebra here, you have supersymmetry, and look at this algebra and its unitary representations, the mass for supersymmetric black holes will be the sum of those 5 charges. So the energy, I was promising had to be a lower bound. The lower bound is this. This is the supersymmetric bound. In the formulae I write, you will see occasionally that there will be a capital N, and that will be just shorthand basically for this combination here of AdS5 radius and Planck constant in 5 dimensions. I'm not actually having an SU N around, but it's the N that would have been the N of SU N if we had a duality, but I'm not emphasizing that at all. I'm doing pure gravity, and then I'm taking L5 equal to 1, sorry. So I'm taking the AdS radius equal to 1, so that all of these, they're kind of like energies. So the sum of the 5 charges is equal to the mass. That's the supersymmetric limit. Now go and look for black holes that do that. What you'll find is that, generally speaking, that's just not possible. You cannot find black holes that have a mass that's equal to the sum of charges. Nearly always, the mass is bigger than that. The only times when you can get it to be equal to that is when the charges satisfy this obscure relation. When the 5 charges are not just general 5 charges. There are 5 charges that just happen to be related in this particular obscure way. If they're not, you simply can't find a black hole that is supersymmetric. And this is an obscure thing, and unlike the example in asymptotically flat, where I said in order to be supersymmetric, take angular momentum equal to 0. That's nice also technically, because you would like to take the angular momentum to 0, because it's the simplest thing to do. Well, here, unfortunately, it depends. If you say simple means spherically symmetric, take the angular momentum to 0. But if by simple you mean supersymmetric, make sure to satisfy this. And that means J has to be non-zero. It may not look so appetizing to satisfy this, but that's what it takes to be supersymmetric, and it's what it takes to make the mass small. So for extremal black holes that violate this, well, they don't have the supersymmetric mass, they have a bigger mass. Papers have been written about that, including by me, and they're not entirely, that are trying to illuminate. It's obscure. It's completely obscure. Some people would say, oh, maybe we just haven't found those that violate this. Those that we know, they satisfy this. No. This is not algebraic. This is a question of, this is the black hole. It's supersymmetric, and you realize that, oh, I should find a 5-parameter family of black holes that's supersymmetric, right? Wrong. I only know about a 4-parameter family. And this is the direction that's missing. So one possible conclusion would be, you just have to work harder. It's the wrong conclusion.
Oh, what is n in this constraint, n?
Yeah, as I pointed out earlier, that since this is pure gravity, I really should write here some combination of G5, Newton's constant, and L5, the AdS radius. So it's a dimensionless version of those. It's a thing that would become the n of SUN if we thought about this photographically, but I actually don't. It's just nice to write it this way, instead of having G5s and L5s, all sorts of places floating around here.
So you are saying you can write this Newton's constant and all in terms of these charges?
Yes.
Like there is some constraint on the Newton's constant and all these charges, Q1, Q2,
Right.
Q3.
Yeah.
Okay.
And I mean, I was saying that we have no understanding. We have some understanding, but a different talk, and not a perfect understanding. Yeah.
Finn, a small question. So is there a sense in which setting this n to infinity recovers the previous flat condition j equals 0?
Yeah, it's actually, now I keep forgetting. I have done this wrong so many times. It's hard. To stay classical, you really would like your q's and j's to be also of order n squared. And that means that this, yeah, so.
But without getting into the technicalities of it, is it known how to take the flat space limit of this condition and recover the previous condition?
Yes, and it will tell you that the j has to be 0. That the scaling is such that when I told you that in flat space, the correct supersymmetry condition was j equals 0. So this thing collapses. And the way this ends up saying that one of my j's has to be 0. Yes. Did I say they were big? You said they were big. And they exist in big and small. There's a phase diagram that has both. That's both a small and a big branch. Like, I mean, these are extremal black holes, so this is not obvious, but it's true. That the phase diagram of extremal black holes actually looks very similar to the Schwarzschild diagram. It has a small and a large branch, and on the small branch, I can take a flat space limit, and in that limit, this thing here, basically q's, get rid of them, and it becomes j equal to 0. Yes. And the actual solutions people are writing that are supersymmetric, you can reduce to a Reisner-Nordstrom black hole smoothly. And yes. So the actual geometry does reduce to well-known, supersymmetric black holes.
So the condition is more complicated partly because it has to simultaneously account for small black holes and large black holes, partly because we have a finite curvature radius, and
I mean, it's certainly the finite curvature radius is what makes it. You have one more parameter than you have in asymptotically flat space. So yes, that's. It's just that when you have one more parameter, sometimes it just is one more parameter.
So the thing, so Finn, the thing that you said that this just describes the supersymmetric extremal black holes that we know, but maybe you should work harder and recover a larger set.
That's a really good idea. I won down at least one student on that one. But
but then when we take that flat space limit of the small black holes, then we recover the previous condition, which also had like a single. So it's not very likely that we'll find the other one.
I mean, look, if you're taking the view, for example, that I should just work harder. Okay, good. Go and find new rotating black holes in asymptotically flat gravity that are supersymmetric. Say the curve was wrong and find a different thing that is supersymmetric. You will not win.
I was trying to voice precisely that intuition, that it's not likely that you will find them because...
Exactly. I mean, just saying that it won't happen. Won't happen. So this is a picture, not the greatest, especially since it's done in colors that are all the same. But at any rate, the idea is that here I have charge, here I have J, and then some curve, which relates Q and J, is down here in the bottom of the valley. This is why the red one here is just getting up so we can see the curve. But really it's a valley. The valley is saying that the mass is bigger than the floor. The floor is if m is equal to 3q plus j, but it's only that on the valley when it's some bizarre curve that depends on q and j. So that's just the phenomenology of these guys. To be supersymmetric, you have to sit on that curve. If not, well, the energy is bigger. Now, that was just my playground. What are the black holes that we have that we can look at? We have extremal black holes for all these charges. Now what? My hypothesis is that extremal, non-supersymmetric black holes are unstable. So let me look at the first law of thermodynamics. This is not extremal. T is not 0. But it's just the first law of thermodynamics. Now I rewrite it and saying this one here is my mass excess, my m minus, okay, sorry, previously it was a j. And there's an issue here whether j is half integer quantized or integer quantized, and it's a function of the parity of the slide number or something like that. But whichever. This is the excess mass, and you have to reorganize things in such a way that you say, okay, if I want to take t to 0 and make this thing here go to 0, actually I'm going to take omega close to 1, as in the rotation velocity equal to 1. I'm also going to take my electric potential at the horizon equal to 1. Now, this thing here, I can use those for any kind of black hole, whether it is supersymmetric or not. Now I'm wondering, if I have a certain excess mass, would it be beneficial for me to, while keeping the same excess mass, to emit something that takes charge away, either J-type or Q-type? Well, what you can see here is that if dJ here is negative, or delta Q is negative, and the excess mass is preserved, it's thermodynamically favorable. Therefore, if your black hole has rotational velocity bigger than 1, this is not bigger than the speed of light. It's bigger than 1 in AdS units. It's not unphysical. It's just a barrier. It's important. It's physically important, but it's not unphysical. It's not faster than the speed of light or something. So if the rotational velocity goes past that barrier, or if the electric field gets too big, then it is thermodynamically favorable to send out particles that have J or Q. We're going to keep the excess mass the same, but we can make the entropy go up by decharging our black hole. So kind of staying as energetic as it was before. It's not going to be supersymmetric, but this way we can do this in a favorable manner. That'll be favorable. So this is a very basic argument. It works actually, this was 5-dimensional, but it works in all dimensions. And there are thermodynamic reasons to believe that if you stay at extremality and you change your charges, you can gain entropy. This is very generic, right? This has nothing to do with some detailed something. And that's good. That means that it's robust. So there are 3 types of extremal black holes. If you actually look among all the extremal black holes, because we know them for all the charges, some are what I would call Reisner-Nordström-like. The constraint is positive. So these charges that some bizarre combination of them have to be equal to 0 in order for this black hole to be supersymmetric. Well, what if the combination of them was positive? That actually is what I would call Reisner-Nordström-like. For example, those particular combination, if I actually simply took the angular momentum away, it would be positive. So if the electric charges kind of dominate the constraint, and the constraint is not satisfied, then you will be in a situation where the electric field necessarily is positive. You can check this on the solution. If you go opposite, if the charges are negative, if this constraint goes negative, the omega will be bigger than 1. Only if the constraint is satisfied, then will both of them be equal to 1. So in other words, either you're supersymmetric and you are exactly at that extremal kind of setup, or you're non-supersymmetric. If you're non-supersymmetric, you're either going to be in the kind of emit electric stuff kind of situation, or emit rotation stuff, and you're going to gain entropy. So you're going to have modes to gain entropy by emitting a particle, classically, unless you are in exactly that situation. There was a question? Yeah. Yes. So it does not happen that this one is positive and that one. No, there is one or the other. I'll give you a drawing, but physical understanding, this is, I think, basically the best I can do. I mean, certainly it's smoothness. In that entire regime, nothing qualitative is happening. And that means that it goes all the way down to where actual rotation velocity is 0. There's no rotation. It's Reisner-Nordström-like. These ones here, it goes over to where it's no electric charge. And it smoothly goes over. There's nothing big that happens. But there's a big thing that happens when these meet, and they meet there.
All of these first 2 kinds suffering from superradiation.
Yes, well, instability.
Instability.
I just said entropy could increase. I did not say superradiant.
Yeah, but
The upshot is that Kerr-like is superradiant. The Reisner-Nordström-like is not.
Is not superradiant.
No.
I see.
Superconductivity.
Sorry?
Superconductivity.
Superconductor. Well, then
So Reisner-Nordström.
you need hair and so on, right? But
Not from superradiant, no. It's to do with where it ends up. I'm here just saying that infinitesimal deformation, I can increase my entropy. But it's to do with where does it end up. And for Kerr, it ends up far away. For Reisner-Nordström, it does not. It stays nearby. So it's kind of, yeah, so it's, you get an atmosphere or you get a ring, Saturn or Venus. Either an atmosphere or yeah, I mean, we have such a process. I mean, well, in AdS3, we have a particularly good job on that because everything can be solved exactly. I don't know. I don't think it's, I don't know. Yeah. You don't throw something in. You just see that stuff that sits on the top basically there's nothing holding it back. There's nothing that, maybe you call it quantum hair production, I don't know. What? What? Hair production. But that's quantum, right? Yeah. But here, I'm just saying that, I mean, I'm not going to show it here, but in the draft paper, at least, we do have the potential. And look, the particle sits on top of the potential. There's no barrier to falling down.
So this is some additional, so you should go on with
Yes, with perturbations. I'll give you a flavor of it. But I'll give you a flavor in a particular technical direction where we have done a lot of suffering recently, and I feel like I cannot do so much suffering without making other people suffer too. So yet, as I say, in AdS3, I knew exactly how to do that. And in AdS5, probably. But it's harder. Yeah.
Do you have any, like the Reisner knots from, can it end up in the BPS through this process, or?
Maybe. I'm not, this is where we need to get hold of Shiraz. He does, I do infinitesimal. He's strong and has an army. So he can, they'll go long distances. So, AdS3 is a particularly good example, actually. We've done a lot in AdS3. I won't show you, but I will just give you explicit formulae because they're a little nicer. So basically, yeah. Maybe, but I mean, sort of. These are probe modes. I'll show them to you, but they're not gravity. Normally, by cross-normal modes, I mean gravity, right? Don't I? Perturbation or gravity. Or do I mean scalar extraneous guys?
We could take a scalar extraneous.
Yeah. Some of those will have. Some of those indeed will have wrong sign. Yes. Some of them will be exponentially increasing.
So maybe that's the answer.
And I'll show you. I'll
Okay,
show you.
so then that's the answer. You take a Klein-Gordon field or whatever field, and you perturb it, and you see it starts exponentially increasing. So that's
I'll show you what the fields are. And it's not gravity. And it's not gravity. I mean, the field.
No, so, but just to say, since it's not gravity, then it becomes a theory-specific analysis. Do you have that kind of a field, et cetera, et cetera?
Yeah,
et cetera?
but.
And so then there's a lot
Yes,
of...
no, there's not a lot. Because at least my theory have to have supersymmetry, else I do not have the right to ask this question. That tells me what my matter is. And that matter will do its thing. Yep.
So you say it is like that?
Yeah.
And then you always have quasi-normal modes.
Well, always. Did I say always? Often, yeah.
My understanding was that the super radius that drives the instabilities in the general analysis of Shiraz, etc., are not always accompanied by the quasi-normal modes which have the wrong sign.
No, I think that's right. I think that's right. Yeah. Yeah. Okay, but look, I will show you the exponentially increasing mode in many, many situations. Not all imaginable situations, but I will show you dozens of exponentially increasing modes. Okay? With wave functions and all. So in AdS3, where I like to have n equal 4 supersymmetry, so the central charge is some number like this is related to the level. I just want to give you an explicit formulae because these are some that are not there, and also just to make sure at least I'm doing something Shiraz isn't doing, because he's saying this can't be done in AdS3, and at least that's what he said in his online talk. And well, we have a paper. So anyway, so here we have angular momenta. We have two kinds of angular momenta in AdS3. One that's within AdS3, so sort of a true angular momentum, and then one that sits within the 5 sphere, in the 3 sphere. The unitarity bound is linear. It's saying the energy has to be bigger than some linear thing that basically is the sum of these two. Depends linearly on both of them. And has a slope cutoff here that depends on my central charge. Basically the minus C over 12 that's so important. That's so well known. But black holes only exist if this happens. Black holes only happen to exist when it satisfies a quadratic constraint. So the lowest possible energy is down here, saturating this. Is it possible to saturate this and that at the same time? Only if the angular momentum has exactly the right value, which is k. So for this, there's a drawing that's quite well known, that black holes sit on a parabola, energy versus angular momentum. And then, well, the supersymmetric range, there are these lines here, the green lines. They touch at a particular spot. It's a little more complicated because there are also these further lines here that are due to spectral flow, but that's not really my point here. My point is actually looking at this line here is linear. It's a supersymmetric line, and that linear thing touches the parabola at exactly one point. And that's the supersymmetric black hole. And in general, there's a lot of room below the parabola, where it's still above the green and red line, so we're still satisfying unitarity, but there are no black holes. So in these regimes, there are no black holes, but unitarity is satisfied. So we should ask in CFT2, what exactly are the ground states of those? And they're not black holes. And we know what they are. But now, this is the old story. Parabola, line. But the new story that I think hasn't been emphasized is that this is not good enough. Actually, this parabola here, you might say, okay, but that's the extremal black hole. So once I get in there, into the blue region, that's my black holes, right? Because they are well in there. They are satisfying my extremality condition. Yes, you would think so, but even though they're extremal, are they stable? Are they stable, the guys that sits on this whole blue curve here, which is the outer part? Are they stable? And the answer to that is no. They're never stable. The non-supersymmetric extremal black holes are just not stable. If you look at the thermodynamic potentials for this, you'll find that they are the equivalent of rotational velocity bigger than 1. So you always have superradiance. In fact, precisely what happens here is very robust, because in AdS3 we know a lot. We have chiral primaries in this theory. I assume we had an n=4 theory. There are chiral primaries. Those chiral primaries, you gain entropy by emitting them. It's not that they carry a lot of entropy away, it's that the guy that stays has readjusted his quantum numbers in such a way that his entropy is bigger. So the full curve is this. Unitarity is a line. Extremality is a parabola. But the superradiant bound is a much steeper parabola. And in order to be stable, you must be to the side of that superradiant bound here. Extremal, you just can't make it there. You can't make it there unless you're at the point that are supersymmetric, which is where everything meets. So therefore, extremal black holes are kind of not a thing. They will be unstable. And we can use this diagram to figure out where they go, because we have thermodynamics on this, potentials and whatever. And as I say, in this case, what is being emitted are individual chiral primary particles. It's very robust. I'm not assuming some bizarre guys. In the CFT2, I need some chiral primaries in a supersymmetric one. Anyway, so that was sort of, that was the first third. No, yeah. Yeah. Well, so I think that in asymptotically flat, it's just less precise. Because were you serious about asymptotically flat? Or did you mean asymptotic flat with some kind of box? No box. Right, but then everybody knows that clearly the ground state in truly infinite space is an infinitely dilute gas. Because that has more entropy than the black hole. It has infinite volume. But it's a little silly, right? Just, oh, no, that's not what I meant. Oh, you meant a box? So therefore, in asymptotically flat, you inevitably end up somewhere like there. And this is why AdS sort of like, that's my box. I am doing a poor job on endpoints. I'm in AdS3, in AdS3 I can do a good job, but in this talk I will not say anything. But here, so it's going to be a black hole, and that basically is follow the line in. So if you're out here, below the superradiance curve, you go parallel to the unitarity line into the superradiant bound. So it becomes a black hole plus a gas. That gas carries very little entropy, and yeah, it carries very little entropy, but it carries some of the quantum numbers. And those quantum numbers are now changed in such a way that the remaining black hole has different quantum numbers and have more entropy because of those different quantum numbers. And all you have to show now is that, can I really have a gas of these guys that can coexist with the black hole while not having substantial interaction energy? And we can show that. And that's in 3 dimensions. It's easy. That's why we're good at it in 3 dimensions, because gravity is sort of not so big. No, it's a gas. Superfluid, superconductivity. We have been looking for that in AdS3. I have, but not been successful, if there is a mechanism like that. We only know about superradiance in AdS3. But we have the feeling that there should be superconductivity as well. But no, but I think it's near instantaneous. I mean, there's no barrier at all. Yeah. It's short. It's short. It's very short. I mean, these are just not stable modes. These are not I don't think they're even semi-classically stable. Right? So they're maybe I'm wrong on that. Maybe you what? But that's still with the exponential, but I think it's worse. You don't need to go back out. You're just sitting on top of a hill, and then you go. I mean, I don't know what the lifetime is. Yeah, I mean, maybe quantum mechanically your time on the top of a hill is finite. I don't know, but it's. So I will talk about superfluidity, not about superradiance anymore. I've just used that as a schematic, but a lot of other people, including gray galaxy people, have been talking about that. So I will go to the other extreme and talk about BPS. So now we have our exponential bound, Breitenlohr-Friedmann. If you take a scalar field with mass m in AdS, write down the Schrödinger equation. It's a standard Schrödinger equation in a 1 over r squared type potential. If the coefficient of that potential is too negative, there is a bound state. And if there is a bound state, that corresponds for this guy here as if there's something exponential. And it means that the time dependence of this thing here will blow exponentially up. If you violate the Breitenlohr-Friedmann bound, you have an exponential mode that will blow away, and there's nothing holding it back. And we can do this quantum mechanically. We can, it really is roll down a potential with no barrier. And the Breitenlohr-Friedmann bound is this one. Standard thing, but I'm just emphasizing it's exponential runaway. Now let's look at what we have in our theory. AdS5, I'm going to, even though in the papers we look at a lot of other theories also, but I'm going to have in mind n equal 8 supergravity, because that's at least an example where you would say it's a sensible thing. Nothing is unstable here. It's a good theory. What should I look for as probes of my black hole? Well, the guys I have in my theory. And I have 42 scalars in the vacuum. I have 20 that have mass squared -4, 10 that has 10 complex that has -3, and 2 that has mass 0. And the m squared equal -4 are particularly important because they are the ones that saturate the Breitenlohr-Friedmann bound. So they're the ones that one would say they are really on the boundary of nearly having a runaway, except they're only at the boundary. They don't have a runaway. So we have these scalars, and I call them T. I don't recall what people normally call them, but anyway, I give them the T, phi, and lambda. Don't worry about the lambda, but these guys I will in fact use. I have different kinds of scalars, T and phi. T are the ones with n squared equal -4. They're on the boundary, phi, not on the boundary. And these guys are in the theory, and I cannot negotiate their couplings and stuff. They have this mass, not just some mass. This is their mass. Now I would like to think about not the vacuum. I would like to think about my Kerr-Newman AdS black hole, possibly with more charges, in n=8 supergravity. That's not what people normally do. They compute the Kerr-Newman AdS black hole in Einstein-Maxwell theory. But I want to compute it in the theory that has 15 gauge fields and 6 tensors and whatnot, many scalars. And I want to consider a setting where my Kerr-Newman AdS black hole is in fact a solution. So I've determined that I want this geometry that I'm familiar with, but I want it as a solution to a theory that I'm less familiar with. And that puts some conditions on my parameters. Basically what I'm going to say is that in a way I have 15 vector fields inside my n=8, and I'm going to pick one of them, a linear combination of the 15, and saying that one is the one that you use as the gauge field for charging your Weissner-Nordstrom black hole. And that leaves 14 other guys. And how should I pick the right one out of my 15? I should pick it in such a way that my scalar fields are constant. They should not drive my scalar fields, because if the scalar fields were not constant, it wouldn't be Kerr-Newman AdS. It would be a different black hole where scalars would be doing their thing, and I really don't want to go find more solutions. I want to have this solution I'm familiar with, which is a standard Kerr-Newman solution, but I want it in a theory that is bigger. That uniquely tells me which of the 15 vector fields I should use. Any constant, actually. Well, sorry. It's not a moduli space. So some of them are moduli. Some of them are moduli, some of them are particular values. You have to take some of them at the bottom of the potential. Some of them at the bottom of the potential. 2 of them can take any values because they don't, it's flat direction. Yeah. But that's the closest I can go in saying it's Kerr-Newman AdS in n=8 supergravity. You know, if I turn scalars on, it would be a bigger space of solutions, no doubt interesting, later. Later, as in years from now. So now then I want to do is fluctuations around the black hole. So I take the fields in my supergravity theory and expand them around the background. Now, since I have picked the field out of my 15, that's the one that's turned on, I can say that my fluctuations around, they will actually preserve certain symmetries. And it turns out those symmetries is an SU3 cross U1 subgroup of my SU4. What this means is that because just of the group theory, actually, that all matter fields, my 42 scalars and the 14 vector fields and some tensors and whatever, many of them have charges with respect to the one gauge field, the U1, the one that's turned on in the background. Because my black hole is charged, and many of my fluctuating fields will be charged with respect to that field. It's set, I can't pick, I can't decide, I just have to work it out. But some degeneracies remain, basically because there's this SU3 global symmetry. It's a little bit like we got 20 fields as a package, and all the 20 were kind of similar. Similarly, I'm still going to get some things that are kind of similar. They're in packages, but smaller packages. In fact, these 20 scalars are going to fall into a package of 8 that are neutral under the U1 that sits in the background, and 12 that have charge that my normalization is 2. So my 20 scalars fall into 2 kinds. And the important part is that they have whatever couplings they have, and those couplings are determined by the theory. n equal 8, I can't mess around with. I have a solution, go expand. And you find that 8 of the fields have 8 of the fields have no charge, 12 have charge plus minus 2. And these are all similar, these 12. Now, that is thinking about things from the point of view of my original AdS5 stuff, but it's worse. Because after all, your background then has sort of a radial flow into the origin. And these scalars, if you solve their equations of motion during the entire background, they kind of change as we're going in. This was called an attractor flow. It's very well understood in asymptotically flat spacetimes. It's very poorly understood in AdS spacetimes. And we have foolhardily spent more time than we probably should understanding such a technical problem, but we have understood it in part at least. But the suffering that is involved is that we are engaged supergravity. Oh, and the radial flow is in a background of a hole that's rotating. Because I really want rotation. Because I want supersymmetry to be part of what I'm considering. Not necessarily, but to the extent I'm interested in Weisser-Nordstrom, I'll say, yeah, Weisser-Nordstrom interpolating to the supersymmetric locus. Right? Or all the way to pure Kerr. So, since I want all that, it takes a lot of work. I will make you not suffer, just saying that we have actually done suffering. In the end of the day, the upshot is that these black holes, these perturbations, in the near horizon region, they're kind of like scalars. They're scalars in AdS2. They're like my Breidenlohner-Friedmann scalar in AdS2. The big thing is, what is the radius of said AdS2? Because that'll depend on the black hole parameters. That's your computation, yeah. Yes? Yes? That's what I will do here, yes. It's the same thing, but in different units. So instead of being -4 being the critical thing, it's -1/4. -1/4. When you have something, a black hole that has -4, mass squared -4, and you say, huh. And now suddenly it's -1/4, that's the critical thing. That sounds dangerous to me. Of course, that's just based on the quote-unquote approximation that the AdS2 radius is the same as the AdS5 radius, which is not true. Why should they be? But that's what it sounds like. And it is what is true. If I take an m squared equal to -4 scalar, put it in my Kerr-Newman AdS background, I will find that the entire red region here is unstable. Unstable in the sense of violating the BF bound. BF bound is violating the entire red region. Down here is Weisser-Nordstrom black holes. Over here, Kerr. Black line, BPS. There's exponential runaway for an m squared equal -4 scalar. This is bad, because, for example, wait, such a thing would have seemed a reasonable thing perhaps to consider as something over here and say, I know, this must be super radiance, very good. It's unstable. Or this must be superconductivity or something is unstable. Really, but once you interpolate, you say, wait, this can't be right, because it's unstable also on the supersymmetric locus. All I did was take in an m squared equal -4 scalar field and put it in the background and see, wonder what mass it has in the AdS2 region, as in units of the AdS2 scale. That's the supersymmetric locus, yes. So, it looks much the same as the Weisser-Nordstrom locus. It's not good, right? Not good. But there's a catch. I took here just some m squared equal -4 field. Just plugged it in because that's what I did. But it's not what I should have done. I should have taken one of these scalars. As I say, they're already in the Lagrangian, and they have one term that's m squared equal -4. That's true, but they have other terms. Some of these are not charged. This is true, but all of them actually have what I call Pauli couplings. If you have the field strength here, there's a kinetic term in front that depends on the scalar fields. And the field strength here, I'm going to expand basically around the field strength that's turned on. This one here has quadratic terms. That will look as if they are mass terms. Phi squared times stuff, and this stuff here in the AdS2 region is just a number. No, because I've solved my equation of motion. Yes. So it's only quadratic, but there's a quadratic term, and they all have a quadratic term. Some have a quadratic term that goes upwards, some have that go downwards. So, you know, some of them has p equal +2, some are -2, but whatever. It is never true that this is just an m squared equal -4 field. So this thing was bogus when I showed you that this was it. That was as if I just said, oh yeah, it must be m squared equal -4. Good idea, but not the complete idea. All right? Yes. Yeah. So that looks bad. One of them will make it worse and one will make it better. That's right. But this is not all. Each of them have two complications. The neutral guys, they have this one here. But it turns out that on top, they mix with gauge fields. Because they're also gauge fields. There are 14 gauge fields. Nobody said that the scalars couldn't mix with the gauge fields. They do. So the neutral guys, they do this, which makes it worse, and mix with the gauge fields, which makes it better. The other guys, they have this coupling with a sign that makes life better, but they also have a minimal coupling. So they all have two complications, in addition to the fact that you had to take your L2 and figure out what the L2 was. You have couplings that are not so intuitive. Fall off. I mean, yeah, you mean, yeah, but I'm here considering, I mean, we've computed this everywhere, but right now I'm using my intuition entirely in the near horizon region. Because if the reasoning being that if it's stable there, it's probably also stable further out.
So you want to say in the near horizon region, you take that value of it, think of that.
Yes. So some of the tricky things, at any rate, are standard minimal couplings. Right? So the 12 T plus fields, they have E equal 2. And they're the sum that's sort of like, okay, good. This is the kind of thing we've seen if we did holographic superconductors. A mu squared, this, it gives a term like this. It looks like a mass term. When we just expand this, there's a mass term, kind of with a mu squared being sort of the mass. And here's a plot of a mu. Down here, near the Reisner-Nordstrom, is negative. It tends to turn the mass more negative, more unstable, so it actually tends to make the black hole, you know, condense, make the scalar condense down here. That's what's well known. What's slightly less well known, I think, is that when you go further up, it changes sign. This thing is stabilizing my Kerr black holes. And stabilizing, in fact, the BPS black holes. So for the Reisner-Nordstrom black holes, a coupling to a gauge field is destabilizing if I'm Reisner-Nordstrom. But it's actually stabilizing when I go rotation enough, and if I go to BPS or go to Kerr. So that's the thing, that the background electric potential, it gives charge scalars an expectation value. This is superfluidity. Holographic superconductors were studied a lot, but I don't know quite if that's true, but I'm saying here, not embedded in full supergravity. That's taken from Sachde's recent notes. I don't know if it's true, but that's what he says, and I think some people have done it, but well, anyway. Superconductivity is down there when sort of black hole is under rotating, when it's Reisner-Nordstrom or a little bit of rotation. Right. So what happens in the charged sector? My 12 T pluses, they had two things. They had my m squared equal -4. That was kind of bad. Then they had minimal couplings, which was bad down here with the Reisner-Nordstrom, but good up here. Then they had Pauli couplings F mu nu, which were the other way around. Well, now you have to go add. They are unstable only up here. So there's a little bit of superradiance. If the black hole is rotating a lot, these guys can get emitted. But it's not a big deal. And in particular, the black line, the BPS, oh, it's very stable. Of course, it's only when I'm considering these 12 T's, right? I'm just saying these are 12 of my 42 scalars. But, you know, that's what I'm considering at any rate. So these were the guys that were natural to think as unstable. M squared was equal minus 4. I take my L2 into account. I'm in trouble. And then I'm like, oh, they're charged. I'm in more trouble because electric. But no, no, no. The signs can be all sorts of things. So all told, I'm in trouble for very highly rotating black holes, which, yeah, I kind of thought they were going to be unstable anyway. So no worries. Okay, but that was 12 scalars, 30 to go. All right, we got others. And one of them is particularly interesting, which are my phi's, the ones that were part of the 10 complex that had m squared equal minus 3. They were not on the boundary of stability in AdS5. They looked much safer. But these guys here, once you embed them and ask, what charge do they have with regard to the actual background gauge field? Well, they're in the 10, and you expand down, and it turns out that 1 of the 10 has charge 3. 3 squared gives 9. 9 is a lot bigger than 4. And therefore, they have a lot of superconductivity. They're being driven negative by a lot if they're in an electric field that's strong. So therefore, down here, they're being driven to be superconducting easily. And it goes all the way to the BPS curve, but it touches at only 1 point. Kind of a good sign, right? If it crossed, something's wrong. If it's at, okay, something may need closer study. But it's kind of what you're thinking, that yeah, it should be unstable pretty much everywhere. So you get superconductivity even when you turn on rotation, only when you turn on so much rotation that you made your black hole supersymmetric, does it go non-supersymmetric. With regard to this particular field, which was not the most obvious field, in retrospect it's the most obvious because it's the one with the biggest charge, but it was not, by the point of view of its mass, the one that looked like the most unstable. But this is the guy that's most unstable. Down here, near Reisner Nordstrom. Yeah, it beats me. So these are very small black holes, literally. They are very small. So it may also be that I should go and say, yeah, but you weren't serious about the small ones anyway, were you? I mean, they're small as in also on the branch structure. So they are. Yes, but the phase diagram, still, you can have charge over n squared and still be on the small branch, the one that has negative heat capacity. Negative heat capacity, these are zero temperature black holes, but there is a notion of heat capacity that we've developed that is such that they smoothly go towards flat space. So that's these guys here for which other stuff applies, but precisely what other stuff? I don't know. You know, we're not done with this, you know, but I hope that it's clear that we have done something. You know, so, and my student graduates this month, so. All right, so this is my picture. This is a cartoon, it's not quite right, but superconductivity down here, superradiance up there, basically omega bigger than 1 in this entire region, which makes me think that it is superradiant in the entire region. We can discuss what it is superradiant with respect to. And I have good candidates in the areas over here, not everywhere. Superconductivity, same thing. I have good candidates where I knew it definitely had to work. I somehow think it probably is true everywhere. But what do I know? So, questions? And this was based on my thermodynamics argument, which is strong because it's generic, but it could also fail because it could depend on exactly what are the particles available to me. Just because I can say that if there were all particles, this would happen. Well, there aren't. So this is where it comes down to what you were saying, that, oh, but in the theory, it's special, whatever. We've been trying to take exactly that into account. But there are theories we have not considered.
There were some regions
where I can actually, yeah, so for each field, right, I can say, okay, this is actually displaying a mode that will go superconducting in part, in a substantial part, but not everywhere, right? And I'm saying, you know what, thermodynamically, I had a reason to believe it should happen everywhere. Now, is that reason maybe not strong enough, and that literally there is some place that should be carved out? Maybe, I don't know. Or, yeah, I don't know, right? I don't know. But big swaths are consistent with this in N=8 supergravity. On both sides. I have big swaths on both sides, but not everything. And those swaths go in and touch. They just don't hug the entire line. Yeah.
Even if you didn't have the right spectrum, as long as there's some operator which meets some kind of bound, there's probably some other mechanism that might not be so easy to analyze classically by just looking at equations of motion, but that says that you still have the instability, right? Because you can somehow, go from one state to another state plus this other operator.
Yeah, I mean, look, I assume as much, I think this is basically true. But it's more like basically true. And I showed you, when I decided to go into some technicality, need to talk you through something, I was telling you about the couplings here that are a little bit non-intuitive and can definitely cheat you about which mode does what. The couplings were harder and less intuitive than maybe you thought. The interplay between rotation and electricity and Pauli couplings, and they do things that I had to plot them before I knew. It's not like, oh yeah, this is definitely positive, and this is negative. Right, exactly. Which is biggest? So I had one minor point towards the end that it is good that I didn't write too many slides because I figured there wouldn't be much time, but that's our last part. I do want to give you just a little bit of CFT. What is going on in a toy model? This is for the 2D CFT, just a toy model. Two chiral 1D bosons with charges plus minus 1. This is their partition function. 1 minus q to the n, but with charge 1. This one here, charge minus 1. So this is well, it's not even a full-fledged conformal field theory with C = 2, but it's kind of, that's the closest thing to a C = 2 kind of theory that we can reasonably say that, yeah, this is 2 times divided by 1/24 in front. Well, so at any rate, if you try to analyze this partition function, which is the partition function of 2 chiral modes with these charges, and saying, what happens, where's my entropy coming from? Where's my entropy coming from? Well, let me go and do my modular transformation to try to figure out what happens when I'm using many, many of my modes. And what we normally get here is that we get some exponential here that in particular has a 1/beta, so it has some linear in temperature kind of term, and that's what we normally would call the Cardy type term. It's not real, I mean, it's Cardy for a C = 2 CFT, not quite a CFT even, so, but that's the sort of thing that we have an exponential up here that is giving us our semi-classical notion of where do we get many states from. We get many states from basically a lot of these guys are contributing, not just n = 1, but n = high. And this sum here, if you take the log of it, it becomes a sum, and that sum is sort of like an integral. Many, many modes are contributing. And that's what the physics is here, and saying these are just exponentially small, and we get a classical term. And then we have some little guys here. sit in front. So this was the cardiolite. The cardiolite is saying, okay, this thing here is what happens. The entropy is energy minus J squared with coefficients here that actually are exactly what would be in a normal n equal 2 CFT. So this is actually good enough for CFT purposes, for the purpose of getting the semi-classical thing there. These are the right numbers even. But that's not what I'm interested in. This is the generic that I would have gotten, and I could make this toy model a bit better with having many, many states, and there are big central charge and stuff like that, and it would effectively do this. Square root of energy minus J squared with coefficients in front that are given entirely by my central charge. And the fact that I have n equal 2 or n equal 4, whatever I have. But what I'm interested in here is to say, what happened here? What happened here? Because I'm interested in things like, what if omega, my spin goes to 1? Or goes bigger than 1. Well, but look, sine pi omega, it blows up when omega goes to 1. And it takes wrong sign when omega goes bigger than 1. Is this real? Well, what's going on here? Is there something actually going on? Well, the entropy at high temperature is this. Basically, it's favorable to spread over all modes. On the other hand, the occupation number of each single mode is going to be much less than 1. This is kind of this gas is classical. We use many, many modes, and we put a little bit in each of them. We actually don't put a lot in any mode. This is classical mechanics, statistical mechanics, actually. And that's my black hole description in this toy model. But if you ask, well, what I really want to do here is that I want to say, I want to go to the lowest possible energy given a conserved charge. And I'm a little puzzled because the lowest possible energy is E equal to a half J squared. But I know, I mean, I wrote it down after all, my theory, right? I have some modes that have E equal to J. Those are my lowest modes, the n equal 1 modes. And I could say, why couldn't I just put a lot of states, a lot of those? And that means I can violate this bound. This bound is a fake. It's a fake that is a fake by using the high temperature expansion in the low temperature regime, which of course you shouldn't, right? But which can work, sort of, for some purposes, but it also obviously can go terribly wrong. And that's what it does. So if instead I say for conserved charge, my ground state energy is J, E equal to J is the lowest possible energy I can get. Because there are particles that have E equal J equal to 1 in this theory. This large charge here, if E is large, they will violate this. So I have a violation, which really is to say, whatever way I got this clearly doesn't apply. But these prefactors here is what will matter in the limit where I'm going to this limit here. And I can go and analyze them and split them up and get a different kind of entropy formula in E equal to minus J, no square. What this corresponds to in CFT terms is really, really simple. It's saying, look, I get many, many states because here I have a free scalar field, 2 free scalar fields. And they have whatever number of many states because I'm having whatever fixed amount of energy, and I split it out over all of them. But if I have to have a certain amount of J, the best way of dealing with that at low temperature is to simply say, oh, you know what? Why don't you take the first J oscillators and just deal with the J by putting them in the 1. It's going to give you no entropy because I'm going to put it in a given state. And that means that what is left is E minus J. That's the energy I got left, and I should do that in an equipetition kind of way. So this is Cardy's formula for E minus J with a shifted J. You can actually do this in fancy ways and call it spectral flow and stuff like that. So this is a thing. I can do this beyond the toy model. But the way I will interpret this is that it's Bose-Einstein condensation. It's because I have a macroscopic occupation number in the n equal 1 mode. Because J is macroscopic, and I decide to use one quantum state to deal with this one macroscopic quantum number. And then I deal with all the others, the stuff that I get a lot of entropy. It's a separate thing. So I actually get phase separation. I have a condensate that have no entropy, but a lot of charge. and I have the rest, which has lots of entropy. This really is very similar, actually, to the picture in emitting stuff from my black hole. And for the AdS3 case, this picture lines up really well. So that's my summary. Thermodynamics really is very intricate. And I've told you a bit about the phenomenology of the black holes, and then about our tour towards trying to investigate specific modes that can be decayed into at various times, and overall trying to argue my point that non-supersymmetric extremal black holes are unstable. Near-extremal too, but especially extremal ones. If they're not supersymmetric, they're unstable. So thanks for your attention.
We have time for a few questions.
Unless you want coffee.
This constraint that you had for the supersymmetric one, is there something similar in AdS4? Or is
Yes.
it just,
Oh, yes.
So it's a kind of a more generic.
Oh, no, it's in all of them, yes, it's in all of them. And including in AdS3. But in AdS3, it's so boring that it's a little bit, there's a little bit like the asymptotically flat black hole, where it's like J equals 0. That's a constraint. It's an equation, but it's a really boring equation, right? In CFT2, it's J equal to K.
So in AdS4, it's a nonlinear constraint.
It looks much like this. It looks very similar. It looks very similar. I mean, at a first sight, it looks similar. But obviously, there's one J and 4 Qs, and then there are these 5 charges put together in a way that's, yeah.
No understanding.
I mean, no understanding, that's harsh, but I mean, some people, I think, believe even that there's a derivation, I just think it's not justified, that if you find the entropy, so the entropy for AdS black holes we have some understanding of, but in the path integral way of doing that understanding, it involves a saddle point that's complex. And then you try to figure out, okay, but how big is my saddle point? And that gives you my entropy. But you've got 2 conditions. You also have a transverse thing. That transverse thing is the constraint. So actually, from that point of view, it's like a complexified entropy. You have an entropy with an imaginary part. And then the condition that the imaginary part is 0 is the constraint. But okay, is that an understanding? I mean, I'm a little bit unfair perhaps to the argument, but not, it's not great. It's not great.
And then when you consider these non-supersymmetric ones, as you said, for the Kerr, it is one sign, and for the Reisner, it's another sign. Is there a sense that maybe this is going towards 0 as you, I mean, is there a sort of,
I quite understand.
The thing when so if you call whatever that constraint is C, then is there, so
I actually call it H.
H, okay, so H less than 0.
And the way I have done my signs is such that this is
so
true, that
phi
over
greater
here
than,
is phi, that's
greater
bigger than 1, and H is smaller, is the other sign.
So is there a sense in which sort of in the instability, the kind of the H maybe has some sense as some function that tracks the deviation from supersymmetry, and maybe decreases.
It does. Yes.
It decreases or something like that.
It does. I mean, so if you're in here, you're near extremal actually. So here, this is strictly extremal, right? So if you're a Schwarzschild person, then you would say, Schwarzschild, what do you do? When it's Schwarzschild, you're interested in things like the modes where energy look like T squared. That's the regime you're in. Yes, but that was in case you wanted, that was when you had in mind, I guess, adding a little bit of energy above your AdS2 limit or something like that. But there's another way to add energy, which is violate the constraint, but stay at T equal to 0. Well, that gives another term. And it has nice coefficients. And they're related by n equal 2 supersymmetry. So therefore, in the regime where this is small, near the curve here, I actually have a Schwarzschild theory for this whole thing, for the 2 sides. And there, this phi here, which is a phase mode, But that's in the microcanonical ensemble, the canonical ensemble, because temperature is the canonical ensemble. This is the corresponding canonical ensemble for R charge. The dual R charge is H. And this you can do a Legendre transform. I can simply say, should I really work with R charges? I mean, I need R charges in my theory. So I would say that H is the R charge, the U1 R charge of my Schwarzian theory. But that only works, of course, when I'm really, really close to here. And then I'll say, yeah, okay, well, then it's bigger. But when it's really, really close, I can think about this, and that is sort of a microscopic understanding, but near the supersymmetric limit. But this is supersymmetry breaking. When phi is not 0, it's not supersymmetric. When t is not 0, it's not supersymmetric. It's just nearly. So does that answer, at least in part, sort of, I mean, that's one limit where you can do better, right? But and then, well, then you're doing one thing here and one thing there, and you're imagining patching them together.
You had this curve, the bottom part,
Yeah.
where you had control, where you had the scalar that charged linearly.
Yeah.
So there you could pretend that was touching.
Yes, this we have not done. That's right. So this we have not done, right. That one would imagine that the supergravity description of this should be possible to link that up to Schwarzian-like things. And this we have not done. But absolutely. And one thing we haven't done is sort of just, I mean, look, there is a phase transition here. But I don't have much to say, other than I can give you the gravitational formulae, but I would like a more, but well, so more work to do.